Hey everyone, so today we're going to tackle a huge question. How and why has the Earth's surface changed over time? We're diving deep into the powerful forces that literally reshape our planet. By the end of this explainer, you'll be able to describe plate tectonics, explain what's happening at plate boundaries on land and at sea, and you'll even be able to calculate and predict how plates move. So let's get into it. Okay, to start, let's use a really simple picture. Imagine the Earth is like a cracked eggshell, and all those broken pieces are just kind of floating on the hot, gooey yolk inside. Now picture those shell pieces as the continents and ocean floors. The key thing is, they're always moving. And that simple idea, that's the heart of plate tectonics. So that cracked eggshell analogy is the foundation for this massive scientific theory. Let's get into what plate tectonics really means and look at the evidence that makes it so solid. So here's the official definition. Plate tectonics is the theory that the Earth's outer shell is broken up into these enormous, rigid plates. And these plates are just floating on a hotter, more fluid layer of rock right underneath them. This single theory is basically the master key. It explains mountains, earthquakes, volcanoes, even why entire oceans open up and close over millions of years. It's a huge deal. Now, this theory didn't just come out of nowhere. Scientists pieced it together from a ton of evidence. They saw how coastlines, like South America and Africa, fit together like a perfect puzzle. They found the exact same fossils on continents that are now thousands of miles apart. They also mapped out these clear patterns of earthquakes and volcanoes that lined up perfectly with the edges of the plates. And they even figured out the age of the ocean floor, which pointed to this one ancient supercontinent we call Pangaea. So here's a quick question for you. Thinking about all those clues, what's one piece of evidence that really clicks and supports that idea that all the continents were once joined together? Just take a second to think about it. Okay, so to really understand how these massive continent-sized plates can even move, we've got to look deep inside the Earth. We've got to look at the powerful engine that's driving this whole process. So here's a super quick review of Earth's layers, just working our way from the outside in. First, you've got the crust that we live on. That's both the continents and the ocean floor. Right below that, you've got the mantle, this huge, slow-moving layer of hot rock. Deeper still is the liquid outer core, and then right at the very center, you have the solid inner core. So what actually gets these plates moving? Well, it's all driven by the incredible heat down in the mantle. This heat creates these powerful currents, kind of like a giant pot of boiling water. These currents, along with other forces like ridge push and slab pull, are basically just tugging and shoving the plates around, keeping them in this constant, super slow motion drift. All right, time for a quick skill check. Based on what we just covered, can you name the layer that's right underneath the plates that helps them move around? Okay, so we know what's driving the plates. Now for the exciting part, where the real action happens. We're talking about the boundaries, where these plates actually meet. There are three main ways they can interact. And trust me, each one creates some pretty dramatic features on our planet. First up, you have convergent boundaries. This is where plates collide head-on. If two continents smash together, you get these massive mountain ranges, like the Himalayas. If an ocean plate hits a continent, the heavier ocean plate dives underneath it. That process is called subduction, and it forms volcanic chains like the Andes. Next, we have divergent boundaries, where plates pull apart. This carves out rift valleys on land and creates mid-ocean ridges in the ocean, where new crust is literally being born. And finally, you've got transform boundaries, where plates just slide past each other. This is not a smooth process at all, and the friction causes massive earthquakes. Hello, San Andreas Fault. So let's think about this in gaming terms, because why not? A convergent boundary is like two players trying to build in the exact same spot at once. The terrain just glitches out, and these huge mountain biomes are forced to generate straight up into the sky. What about divergent boundaries? Well, that's like when a world sea generates a massive ravine. As the chunks of land separate, new blocks, in this case molten magma, rise up from deep inside to fill that gap and create brand new crust. And transform boundaries, these are just like those awful jittery lag spikes you get on a crowded server. The two land chunks are trying to slide past each other, but they get stuck, building up all this pressure until suddenly the game catches up and everything snaps forward in a massive earthquake. All right, another skill check for you. Thinking about how new crust is made out in the ocean, which one of those boundary types would you expect to find at a mid-ocean ridge? So we've seen the pretty dramatic effects of these plate movements, but you might be wondering, how fast is this actually happening? Well, believe it or not, we can actually measure this stuff and even predict their movements pretty accurately. Let's look at the map. So the speed of these plates, it isn't exactly fast and furious. Most of them are only moving a few centimeters per year. To give you some perspective, that's about as fast as your fingernails grow. It's a really powerful reminder that geologic change happens over a very, very long time. But, and this is a big but, those tiny movements really add up. For example, if a plate is moving just 5 centimeters a year to the east, over the course of 10 million years, it's going to shift about 500 kilometers. That's a huge distance. And this perfectly illustrates one of the most important ideas in geology. In fact, say it with me. Tiny yearly moves add up to huge changes over geologic time. Okay, I've got a practice problem for you to try out. If a plate moves 3 centimeters per year to the south, how far south will it travel after 20 million years? Go ahead and crunch the numbers. So, we've covered the what, the why, and the how of plate tectonics. Now let's zoom all the way out and look at the grand impact. How has this constant movement shaped the world we know today? And why does it even matter? Well, over millions and millions of years, these plate motions have completely reshaped oceans, they've built massive mountain ranges, and of course they cause earthquakes and volcanoes. But it's even bigger than that. The shifting continents change global climate patterns, and they even influence how life evolves. Plate tectonics is really the engine behind Earth's entire long, dramatic story. All right, one last check to tie this all together. In a single sentence, can you explain how the exact same process, plate tectonics, is responsible for creating both the highest mountains on Earth and the deepest trenches in the ocean? And that's plate tectonics in a nutshell. It's slow, it's steady, and it is monumentally dramatic. If Pangaea were a canceled streaming series, plate tectonics would be the director, just rewriting the entire map and introducing crazy new plot twists every single season. So that's our look at plate tectonics. If you enjoyed this explainer, make sure you like and subscribe for more. And hey, drop your answers to those questions in the comments or in your notes. I'd love to see what you came up with.